Okay, so let's get started. So the topic I chose for this presentation today is on the screen, and you might feel that I am really being very greedy, right? It's not enough to be resilient for infrastructures. We also want to be durable. I want to be durable, low carbon, cost effective. And not only that, all at once. That's the key word here, all at once, right? Okay, because there are lots of research. The reason why I choose these wordings here in the title is because there are a lot of research going on resilient materials or more likely high compressive strength materials. Somebody work on UHPC, right? High compressive strength material, does it translate into resilience in infrastructures? That's the question I want to raise. Does it help in terms of durability? Can it reduce emissions of carbon during construction and during the use phase, the service life of the infrastructure? Is it cost effective at all? So we want all of this to be in a single material, not in separate materials. That doesn't really help our infrastructure. So the key word here is infrastructure that we want. Right now, it doesn't work. We are not there. We have actually spent a lot of time and done a lot of research. You can see this in the next slide. So since the beginning of modern concrete, of course, you can trace back even further to Egyptian times and so on, but I'll skip all that really long history. But the modern concrete has actually gone through a lot of development. So reinforced concrete, reinforced of steel, rebars, pre-stressed concrete, and so on. Those are recognizing the fact that concrete is brittle. It doesn't like tension. It enjoys compression very much, but not in tension. So we need the steel to help out. And that actually makes concrete useful and help us in terms of developing our industrial economy. All our modern infrastructures are based on these concepts. So those are very important developments. High-strength concrete, believe it or not, started in the early 1950s, still going on today. UHPC is an example of that. Typically, high compressive strength is what is aiming at. But again, my question is, does it really translate into resilient infrastructures? Noticing that when I say resilient, and I'll show you a picture in a moment, let's take earthquakes as an example, right? Under strong earthquakes, severe loading, we still see building collapses. And it's not because of lack of compression. It's typically failed by tension, cracking, fracture, right? Those are all tensile deficiency. So there is work cut out for us. Self-consolidating concrete is actually very important. I actually saw it being developed when I was a visiting professor at the University of Tokyo. Professor Okamura led a research group there. They call it self-compacting concrete in those days. I believe still so in Japan. They were the leaders. And I remember that because I was on the visiting faculty there, and I saw teams of engineers from the big companies like Shimizu, Taisei, and many other big construction companies sent their people to campus to learn how to mix those materials. That was the beginning of self-consolidating concrete or self-compacting concrete. Later, it transferred technology to Europe, and the US was the last one to adopt. Now it's everywhere, right? So this is an important development, and it's developed because of, does anybody know why it was developed? Self-compacting concrete or self-consolidating concrete. What was the motivation behind? Anyone? Yes. That's called self-healing concrete. I'm talking about self-compacting concrete. You have it. Okay, so that's exactly correct. Yeah, so the lack of reliability of construction, the lack of high quality labor, I was told, right? That was the driver behind this material. So they are able to construct very well, but only when you have high quality labor on site. And not every time, every case is like that. So that creates infrastructures that are not sometimes not so reliable, not as high quality as desired. That was the motivation behind. Fiber reinforced concrete, again recognizing concrete is brittle, so uses fiber to try to control cracking. Started in the 1990s, still going on, as you'll see. Self-healing concrete, somebody pointed out self-repairing. So this is a good example of smarter versions of concrete that can do things itself to help the health of our infrastructures and reducing service repair requirements. Geopolymer carbon capture reflects our modern day desire to green our infrastructure. So you can see that developments in concrete has been going on, has never really stopped over the last 200 years or so. And a lot of advances has been made, important advances. We need to recognize those accomplishments. They are real, and they help us get to where we are today. But are we there yet? And behind this question is, can we really create resilient, durable, low carbon infrastructures? Notice that my question did not ask, can we make strong concrete or green concrete or durable in the laboratory? I said, can we make resilient, durable, cost-effective, low-carbon infrastructures? Why? What's the distinction between those two? Do you use concrete every day on your way to school or to your office? Or do you use a bridge? Do we live in concrete or do we live in a building? Yeah, so we users are using the infrastructure, the building, the bridges, the roadways, and the dams and the tunnels and so on, not concrete, right? So what is most important is when we talk about resiliency, durability, and so on, we should be referring to thinking about the infrastructure, not the concrete material, and especially not the concrete just in our laboratory. And behind that wording, I'm suggesting that sometimes it works beautifully in the lab, but not when it's outside in the real road, in the real world, when it's being used, when the infrastructure is exposed to life loads and environmental loads. But that's what we need. Agree? Okay. So again, take a quick look at the next picture here, the next slide here. And we see what I just mentioned. We still have collapse of buildings and lack of durability, especially for infrastructures that are near the coastal areas exposed to aggressive environments. So these problems still remains. In fact, this one here on the left-hand side, or your left-hand side, is the collapse of a building just last year in 2023, 2 years ago in Turkey. So this is designed according to the new building code already. And yet you see, and what I'm trying to show you, I choose this picture because it's clearly show a fracture here, okay? This portion of the column did not fail, but you have a sharp fracture despite the steel reinforcement inside. So this is telling us that one of the remaining deficiency in concrete technology is that the material, despite all the developments over the last 200 years or so, remains brittle, okay? Now take a look at the right-hand side here of the screen. This is a crack, obviously, on the floor slab, most likely a parking garage area. And this is lack of durability. And subsequently, you get corrosion of the steel rebars inside and so on. Again, if you think about what's the basic problem here, cracking, fracture, these are related to lack of ductility of the concrete material. The concrete is brittle, leading to lack of resiliency and lack of durability. So now we have a possibility What if we can make concrete that is ductile, that is no longer brittle? Then we have the possibility of overcoming danger or lack of safety of infrastructure and possibly creating infrastructure that can last for a very long life with little or no maintenance. That's what we should be aiming at when we think about researching in construction materials, think about how it's applied, what the conditions are out there, and not just in the laboratory. Okay, so to summarize, we need to develop a new kind of concrete material that addresses all its deficiencies. So I already say that, so I won't belabor that too much. But here I do want to say that we should be testing under field conditions as much as possible. Some of you may argue that it's not very practical to test in the field, but we want at the minimum testing in the lab that simulates the real world conditions as much as possible. Okay, and I'll explain that a little bit more in a moment. We want to consider both the installed as well as the long-term cost, right? So the initial cost is important. Otherwise, the client, or construction company, or the owners may not buy it, your design. But the long-term service life also, especially for infrastructures which has a very long service life, typically 50 to 100 years. I just wrote a few days ago, the Hong Kong, Macau, Zhuhai Bridge, right? That bridge is designed for 120 years service life, right? So infrastructures are notorious in the sense that it's designed for a very long service life, different from my cell phone, which probably, well, actually this is unusually long, 6 years, right? But most people have much shorter service life for their cell phone and becomes obsolete. It is already obsolete. So we can repair those if it deteriorates, but our infrastructure, we have to keep them. We can't replace them. And repeated repairs is very common in our industry. And that's expensive, not only in cost, in dollar terms, but also in environmental terms. And of course, you and I have the experience, I'm sure, of traveling in traffic, stuck in traffic for a long time because of construction or reconstruction events, right? Repair events. So all those are non-desirable. I'm talking about all of these things. You think I'm not an engineer. I am, but I engineer for human. I don't engineer for just the concrete. I'm thinking about the infrastructure that people use on a daily basis. That's what we want to strive for. Okay. Okay. So the last point here is that can we actually design a new kind of concrete that would allow us to have the desirable resiliency, safety, durability, long service life with minimum maintenance, sustainability, low carbon emissions, both in the install phase as well as in the long term. So let's take a step back and say, what kind of concrete are we looking for? We want a concrete that is damage tolerant. Damage tolerant means that even under extreme load, you can damage it, but you don't break it. It doesn't collapse, right? It can suffer damage and then hopefully even repair itself, or with minimum repair, it goes back to service. Okay, so the current concrete does not do that. It either is completely intact or when it fractures, it really fails. It just gives up, okay? So that's because of the brittleness I already said. So we want our new concrete to enable structural members that are ductile and sustain low capacity, even in earthquake loading when it's severe, and yet even under damage, it still holds up, okay? And then quickly repair. I'll talk more about this with examples later on. We want a concrete that has high durability, and right now, concrete cracks too easily, and then subsequently you have corrosion of the rebars and so on. So new concrete should lead to infrastructures. Again, I'm emphasizing the structure that maintain durability, not just the concrete itself in the loaded condition in the field. Okay, so I hope that's clear. So finally, carbon and current concrete suffers from high operational carbon. So this is a keyword here, operational carbon. What do I mean by that? Sometimes we say, when we use that word for other products like a refrigerator, operation means the electricity that is needed to run that appliance. In this case, if you're thinking about a bridge or a tunnel or roadway, that doesn't require electricity. So what is the operational carbon? Well, that's what I just mentioned, the carbon associated with repair events, with repeated repair events. And the tailpipes emissions that are associated with vehicles that are stuck in traffic because of repair events. So all those are related to the quality of our infrastructure. So this is a very big calling, asking, can we develop a concrete that do all of these things different from current concrete? Okay. Is that clear? That's what we are looking for. Okay, so what I am suggesting, and there are many research groups now around the world carrying on research in ECC, or the long word is engineered cementitious composites. Okay, it started in my laboratory in beginning way back at MIT, and then subsequently we developed the material and applications at the University of Michigan, but now it's carried out by many of you actually in the audience who are doing research around the world. In Europe, in Japan. Japan actually is one of the leaders in applications now. They have emerged as a quick applicator or user of this material in the real world. I just traveled back from China. I spent a month in Shanghai, and I saw a lot of different applications, over several thousand cases of retrofit of houses, masonry houses. So there are lots of different applications going on. So this material, for some of you, it may be new, so I will spend a few minutes talking about that. So it's very different from normal concrete, or even here in this piece, this is a high strength concrete, put it under bending load, and suddenly it breaks into two parts. That's what you expect of a brittle material. So an easy way to understand that would be like putting a slab of glass and then try to bend it, and then it doesn't do anything until it goes bang, and then it breaks into two parts, right? So that's the brittle behavior we are very familiar with. But with the ECC, you can bend it to a smiley face shape, and it's still holding the load. Okay, so this is the main difference of ECC compared to a normal concrete. If you look very carefully on the tensile side of this slab here, after it has been bent to this shape, you'll see micro cracks, very tiny micro cracks on the bottom side. So this is damage, okay? So I have deliberately damaged the material by exerting an extreme loading to a very large deformation, and yet it did not break into two parts. Okay, it's still holding the load. So this is a good example of what I meant by damage tolerance. It's the material is damaged when it's under extreme load, but it still carries the load imposed on it. Okay, so compared to familiar materials like concrete, if you pull a piece of concrete in tension, you have the elastic phase, and then suddenly a crack forms and the load drops to zero. So this is the common brittle fracture behavior of concrete material. If you put fiber in the concrete, you get a fiber reinforced concrete that after the first crack forms, you have tension softening when the fibers get pulled out or brick across the bridging across the crack. As the crack opens up, the fibers are pulled out and that or fractured. Okay, and What we are looking for is this behavior in green. We have a strain hardening behavior. Even though the material is damaged, the load carrying capacity continues to rise. And how far, how much? Well, a good way to measure is this number, tensile ductility. When does it begin to descend, this branch descend? And in this example here, for ECC, it typically goes from 3 to 5% tensile strain. And some of you, including Professor Dai, has shown that you can even push this even further. And what is different from conventional concrete and for FRC is that this peak point for these two materials happens roughly at 0.01%. So this tensile strain capacity, we are talking about not just 2 times or even 10 times, it's hundreds of times more. So it's truly ductile. And that's why you see that curvy face facing at you when you bend that beam. And that's what we expect our infrastructures to do when it's put onto a building, for example. And when that building is subjected to severe earthquake loading, you want it to deform, damage, but still hold the load so you have a chance to escape. You don't want that beam or column to suddenly snap into 2 parts. You have no chance, right? So that's the safety resiliency concept I was referring to a moment ago. Okay, so just now I show you just illustrative tensile stress strain curve comparing those 3 materials. These 2 are real test curves. This is a common normal ECC with a compressive strength of 40 megapascal, not particularly high, but showing the very large strain capacity over 4% strain before it finally fails. The blue line here shows a UHPC, which is famous for its high compressive strength, over 200 megapascal. And it does have some tensile capacity after its initial cracks, although typically the strain capacity is less than 0.2% rather. So it's limited ductility, very high compressive strength. If necessary, and Professor Dai's group, I believe, has produced also this kind of high strength ECC. ECC with high ductility, that's typical of all ECC. That's the common factor for all members in the ECC family, but you can actually also get high compressive strength as well. I just came back from Shanghai. That group I was visiting is Tongji University. They also have produced very high compressive strength ECC. Actually, they use it in a 2-story building and test it in a shake table, and it works beautifully. The most amazing thing is there are no steel reinforcement inside. It's 0 steel reinforcement. It's totally dependent on the ECC. Okay, so I wouldn't go and design buildings, especially like 60-story building today with that. We need to accumulate more experience, but it demonstrates that those ideas are feasible. That ECC is a material that itself have resiliency, and that there are situations when we can diminish or reduce the amount or even eliminate steel reinforcements. And there are many good cases where you want to reduce or eliminate steel reinforcement. For example, one of the major lack of durability of infrastructure is corrosion of the rebar. If it's not there, it cannot corrode, right? If you don't use rebar in the ECC, there's no corrosion problem because it can't happen. It just cannot happen, right? So there are situations when you want that to be in the design phase. Okay, let me, I'm being a bit slow here. Okay, so this is another actual test curve of a normal strength ECC. And you see the bumps going on. Every time there is a bump, it forms one of the micro cracks. So these micro cracks are very, very tight, and they are called, that's the reason why they are called micro cracks. And on this line here, this curve here tracks the opening of one of these micro cracks. And you can see that as I strain the material in tension, pulling the specimen in tension, going up to 1% strain, which is very, very large compared to concrete, normal concrete when it fractures at 0.01%. So it's 100 times that. And the microcracks, width of the microcrack increases up to about 60 or 50 microns here on this axis. And then remarkably, look what happened. After that 1%, when you continue to strain the specimen, even up to 4%, the microcrack width maintains more or less constant at less than 60 micron. So how large is 60 microns? Can anybody tell me the size of our human hair? What's the diameter roughly on average speaking? How many? Several micron. Okay, that would be any other guess? 20? 10 to 20? Okay, that would, I believe there are human beings with those very, very fine hair. But typically on average, it's about 100 micron. Okay, so 60 micron is roughly about half the size of human hair, roughly speaking, right? So it's very thin cracks, truly hairline cracks, right? And what is remarkable is that these cracks maintain their width. They don't open up anymore, even when you strain it to several percent strain. Okay, so and more recently, we developed versions of ECC, and this is showing at different strain levels, 0.5% strain. Later on, increasing the strain to 3% and then up to 5%. You see more and more of these micro cracks develop, and we measure the width of these cracks. Let's move directly to the lower plane here. At 5% strain, very large strain before it finally fails, the micro crack widths are roughly about 15 to 20 micron. That's really tiny. You have to use instruments to look for them, right? They are very, very tight crack widths, and that's the reason why these special techniques are used to detect the width of the cracks, because they are hard to measure. Now, what is even more remarkable is when you make the crack so tight, look here, if only I can activate it. This is a specimen that I have deliberately damaged and then exposed it to air and humidity. So these cracks repair themselves. Okay, there is a chemical process going on. It's very, very simple. It's not any secret here. It's just continued hydration of the unhydrated cement grains. And there are some carbonation effects because the air has carbon dioxide. So there are calcium carbonate crystals inside there when you look into the material. But what is also happening, what it also helps the specimen to not only repair superficially or visually, but it actually regains mechanical properties. You can reload this specimen and it can carry load, okay? Sometimes we have even observed situation where we have a repair crack here. We reload this specimen and yet it creates a new crack adjacent to it, meaning that the repair crack is stronger than the intrinsic material. So this is very important, and this happens because, or at least we think, and I hope some of you will carry out research on this, more detailed research on this. We think that the fibers are actually helping in terms of doing this self-repair job. How does it help? There are lots of fibers crossing the microcracks. These fibers themselves are very tiny, so they are roughly about 30 micron, depending on whether you're using PVA fiber or PE fiber, down to about 12 microns. So you can get thousands in a very small square centimeter cross section. There are thousands of fiber crossing it. So if you look close enough, you actually see a forest of tiny, tiny tree trunks crossing, right? There are many, many of them. And the crystals, the growth of those repair materials, they often start on the fiber surfaces. So they start growing around the trunks, and then they connect themselves together. And then they fill the whole crack. It's absolutely amazing. Okay. And I think that's in a big way helps the integrity of this repair. You can actually make concrete do this kind of self-repair as long as you press the concrete back and then expose it to favorable conditions, especially modern day high-strength concrete when you have a lot of unhydrated cement grains. You can do that, and they would reheal. The problem is, in general, for normal concrete, cracks can be very large, right? Even with steel reinforcement, it's not going to be less than 60 microns or even 20 microns that I showed you, right? It will be hundreds of microns. And then there is no way to regrow those materials that fills up the whole gap. And there are no such forest of fibers I was talking about. But I'm just making up a story for you. For those who are serious, carry out research. This is very interesting research problem. The mechanism behind self-healing in ECC. Okay, so tight crack widths, who cares, right? Durability, penetration of water and so on, resistance to those are very helpful in self-repair, I already mentioned. Now this plot comes from data that I collected, my students collected, I should say, from the literature. And there are many different sets of data. You can see that there are data related to the permeability measurements, iron diffusivity measurements, corrosion of steel, loss of weight of the steel after corrosion, and so on. So in order to put it on the same chart, I have to normalize it. Normalized by the level of degradation at very tiny crack width. Okay, and very interestingly, you see the degradation stays almost flat. All these curves are very flat, doesn't change very much until it gets to a crack width about 0.1 or 100 micron. Above that, you see that the degradation shoots up very fast. Okay, so we were surprised by ourselves. This is a nonlinear process. Degradation simply accelerates nonlinearly as the width of cracks increases. And especially that there is an elbow point here at about 100 microns. So obviously for us, we want to keep our cracks intrinsically tight to less than 100 micron, let's say 50 micron or less in this region. That's what we aim at for ECC. So ECC has naturally tight crack width that do not require external intervention. You don't want to close the crack. You can't do that on a bridge deck. Every time there's a crack, you try to close it. You want it to be intrinsically tight, allowing very little or zero degradation. Okay. Now, what is also interesting in this chart is the ACI code, the building code 318, at least the older version, used to have a specification of crack width limit. And it's about here, okay? It varies a little bit left to right, depending on whether the structure is indoors or outdoors. There are two different specifications, but roughly it's around here. And what is interesting, and the reason why I point that out here is this is very close to the elbow point. So sometimes you can design infrastructures that are below that point, so you are out here, and degradation is very small, so they maintain very well. But just a little bit above here, then you get this very fast acceleration degradation. And this is the problem, a lack of reliability. Okay, and this is the reason why this crack width limit is no longer specified. Why? Because structural engineers complain they can't design in a reliable manner. They can be legally liable if they lose durability, but they can really control the crack width in steel reinforced concrete. So right now, the newer versions of ACI change that wording to specifying the spacing between reinforcing bars. That's easy to measure, right? But there's no guarantee it will be durable. I actually saw a case which illustrates what I just mentioned, and that is a two-way bridge in Florida. obviously very close to each other, built at the same time. And in one direction, everything is perfect. It's durable and everything. The other direction deteriorates very fast, okay? But it's built by the same builder, same material, under same weather condition. And I believe that the reason behind that very strange phenomenon is that it is very close to in this range here. The crack widths can sometimes be a little larger, a little bit smaller. It may be affected by the temperature or even the humidity conditions during casting and so on of the concrete. And that can easily push your material from a safe to an unsafe region or durable to an undurable region. Okay, so the point here is that structural integrity can be achieved when you make your concrete material self-tight crack width that are self-maintained and don't rely on anything, external human intervention or reinforcement, steel reinforcement. You just rely on yourself, okay? So that's the best way. Okay, so there are data that supports what I just described to you, and this is done by our group. We make a piece of the specimen. Remember I said that durability tests, even if you do it in the lab, should simulate field conditions. So we actually simulate field conditions by preloading the specimen in the intention, so it creates micro cracks after preloading condition, and then place the specimen under a hydraulic pressure. Okay, so that forces the liquid, the water in this case, to go through the specimen, especially going through the micro cracks, and we collected the water on the other side of the reservoir as a function of time, and then deduce the permeability. Now, what this chart shows is the permeability measurements as a function of the width of the cracks. And you can see that for the ECC specimen, they all cluster below 100 microns. And that's because the material self-limits its own crack width. No matter how much imposed load I put on, the crack width is tight in ECC. So they're all in this region here, below 100 microns. Now, for the other data, some of it come from our lab and others from other people's lab. I believe a lot of the data came from Professor Shru Shah's lab, where they did permeability testing of concrete specimens that has been preloaded to different crack widths. And you can see that these curves is showing very rapid rise in permeability. This is not a linear chart. This is a log chart here. So every step here is increasing by hundreds, okay? So from here, 10 to the minus 11 going to 10 to the minus 5 is 6 orders, 1 million times higher when you increase the crack width from, let's say, 100 to about 400, 500 microns, okay? So that is very, very fast penetration. For normal concrete, you are typically operating in this range, and you will let water get through very, very fast. But for ECC, because of the self-controlled tight crack width, water permeation is very slow, and that means that it will take a long time for water to get to where the rebars are, even if you have the rebars inside. So it will take a long time to travel through the concrete cover. Okay, so what about corrosion? So by ion diffusion, chloride ion diffusion, we did the same kind of experiment, preloading the two specimens under different deformation, imposed low deformation. And in the case of the mortar beam or slab, as we increase the beam deformation, you increase the crack width. That's what you expect, and there's only one crack there, but opening larger and larger. In the case of the ECC, even as we increase the deformation of the beam, we maintain very tight crack widths and with increasing number of micro cracks. Now, when we plot the diffusion coefficient, so we put a specimen under a concentrated sodium chloride solution and measure how far the chloride ion penetrates into the specimen over time, we deduce this effective diffusion coefficient and plotted against the preload deformation. For the case of the ECC, we saw a linear increase, and this is reflecting the increase in the number of cracks as we increase deformation. But in the case of the mortar, we see a highly nonlinear accelerating increase in the diffusion coefficient. So this is describing to us that it's very dangerous to have crack widths that are large. It actually rapidly increases diffusion coefficient and causes corrosion in a much shorter time compared to that of the ECC. So these are experiments carried out in the lab, but we try to simulate the field condition by preloading the specimen before we run the permeability or the chloride ion diffusion tests. And they demonstrate why the data that I showed you a couple of slides earlier, why it is possible to maintain very good in durability, because the material self-limit is crack width. Okay, so if you don't believe what I just showed you from our laboratory, this is another experiment carried out by a group in Japan, actually quite some time ago. And they did a very interesting experiment. They put two beams and then below them with this rebar, with this bar, a steel bar, with nuts there, with a steel in between those two beams, causing tension here and tension there, and keep the cracks open there, and then expose the whole specimen assembly to a accelerated chloride environment. Now, for the beam, for the reinforced concrete beam, there is only one crack, and the corrosion of the rebar, after they pull open the specimen and look at the rebar there, they saw a large amount of corrosion debris in that rebar, and the measured corrosion rate is very, very high. Okay, just at one spot, but very, very high. In the case of the ECC beam, they see corrosion spread over a length of the rebar, and that's because you have multiple micro cracks, but the corrosion rate is very, very low. Okay, so this is another confirmation that we can expect high durability of infrastructures when we use ECC that has intrinsically very tight crack width. And I show this because just before I retired, there's a group in Virginia, and they contacted me and showed me that they were doing a test of using ECC in the context of bridge decks. So apparently they like this kind of arrangement where the bridge deck is created by assembling these steel box beams, connecting them with shear keys along the joint here, along these joints here. And typically they would then grout these joints with a non-shrinkage grout. And that's used as a control in this experiment. And they adopted two new materials, UHPC and ECC, in the other two joints. So this whole assembly was then exposed to the natural environment. And what is interesting is that they monitor leakage of water from the underside of this bridge deck. And the ECC was the only one, they told me, that there was no leakage at all. And this is not surprising to you now, because the material, even though it can experience very high shear loading at the joint, where the adjacent beams can move relative to one another, the crack, even if it damaged the material, the crack width becomes very tight. And not only tight crack width, but they repair themselves. Okay, that is not the case with UHPC or with their conventional high performance grout. The UHPC with very high compressive strength actually does not help. High compressive strength, this is not a case of compressive strength, right? It fails because it lacks durability due to water leakage. And that's what they want to stop. Okay, so here is another application also in Japan, in a reservoir, and this dam, called the Hitaka Dam, was retrofitted with ECC on the upstream surface, and using a sprayed method, applying the ECC on the upstream. And the reason behind this repair or retrofitting was the observation of erosion of the concrete, and they were worried that water gets through faster and faster through the dam, eventually causing damage to the villages below it. So this works out very well. So far, it has held up, and not a case of durability confirmation in the field. Okay, so I also talk about resiliency, and we can see a couple of examples here. This is a test carried out by the Building Research Institute in Tsukuba City in Japan, and they deliberately caused a fully reversed shear load on the beam section, and these are the low points. And you can see that compare the failure mode between the standard reinforced concrete beam and the reinforced ECC. So in this case, it has the same amount of steel reinforcement, but that failure mode is very, very different. You see the expected diagonal micro cracks. This diagonal because the load is fully reversed. So it's tension in one loading cycle and compression in the other. And then you form the other diagonal cracks. Same here, except that these cracks becomes very large in the case of the standard reinforced concrete beam, so large that you get spalling on the cover and exposure of the reinforcing bars. Okay, so this is not what you want. And if you are a structural engineer, you would particularly pay attention to several things here in the hysteresis loop. One is the peak load before it fails. So obviously, in the case of the ECC, we were able to increase the peak load to a higher level. But not only the peak load, but also the peak deformation is larger compared to the two cases. Now this loading, so you have a delay in failure, and subsequent to failure, you have a degradation, the low capacity. If you look at the envelope of this hysteresis loop, it drops relatively fast. In this case here for ECC, it actually maintains very stable hysteresis loop, and you would want that, right? So this gives you a much larger deformation capacity and resiliency after the initial damage. Not only that, you have much fatter hysteresis loops, suggesting that it can absorb more energy. Now, in fact, this beam was tested exactly for that last point. And that last point was, can we use ECC beam to absorb seismic energy during the loading of an infrastructure? And it was applied to these buildings. Okay, so I'll skip the original design, but this is a new design with the ECC 4 pieces in yellow color on every floor of the ECC. They call coupling beams. They couple the green color core wall. Okay, and they experience extreme shear loading during the seismic loading of this building. Okay, and it has worked out very nice. So these are the pictures taken from the precast yard. So this is the precast beam just installed before they put the core wall around. And I took this picture. I was invited to visit this building in Kitahama, and you can see the coupling, ECC coupling beams in the elevator shaft in the middle, the core of the building. This, by the way, is the tallest residential tower, over 60-story, in Osaka, in Japan. Okay, so the reason why they use this ECC beam is to absorb energy and stabilize the building when the building is shaken by a large earthquake. So far, it has not really experienced a major shock right in Osaka. although there are earthquakes as always, nearby, and it has held up so far. So this is a demonstration of field use of this material for structural resiliency. Okay, so let me switch because of the lack of time. I'll just move on to I'll focus onto environmental impacts. So we want to lower our carbon footprints, and I already mentioned operational carbon. There is also the embodied carbon, obviously embodied in the material, but I want to pay attention to the fact that we want to really look at embodied carbon in the infrastructure again, not just in the material, okay? What's the distinction between those two? The distinction between material, carbon in the material, and carbon in the infrastructure. Well, the difference comes from the fact that the infrastructure not only uses the material, but also has dimensions and geometries, right? So if your performance, mechanical performance, ductility, and so on, allows you to use less amount of material to carry the same amount of load or more, then you actually can come out with infrastructure, a bridge, a roadway that has lower carbon than otherwise, right? So focus on the infrastructure. That's what we want. We want to create green infrastructure, not just green material, right? So let's focus on that. This is carried out by the way, this Professor Dai, this is created, guess who created this image? Somebody I mentioned to you in your office just now. No, Michael Lepek, yeah. So Michael Lepek was one of my former graduate students, and he did a lot of interesting things, but this is one of the projects he carried out. He's now a full professor at Stanford University in California. So he did this work. It's part of his whole PhD thesis, and the work was motivated by the Department of Transportation in Michigan, where they have a lot of problems for their expansion joints on bridge decks. So they have to repair it almost every year when you have joint problem failures, cracking, and so on. And they want a more permanent solution. And what we propose to them is to take the conventional expansion joint away and then also remove some portion of the concrete deck nearby there and replace it with a ECC link slab. Okay, and the idea, and see if I can show that, hopefully the animation works. There we go. So obviously we are making use of the tensile ductility of the ECC being able to stretch during the expansion and contraction of the bridge responding to temperature cycles. Okay, so he actually made these schematics when he was a young man, and it was implemented. I believe one of these is Mike somewhere here, but this is a bridge near my office in Ann Arbor. If you had come to visit me in Michigan, most likely you'll travel under this bridge because this is the highway connecting the airport to Ann Arbor where I live. And the deck and the bridge deck was right there. And the expansion joint, the ECC link slab was placed like this. This is just shortly after reopening to traffic. And it was placed, I believe, 2005. So it's 20 years. It's still working. Durability? Well, at least somewhat proven. It's not 100 years yet. It will take way beyond my retirement. But that's what we are hoping for it to last very long, to minimize service requirements during operation of that bridge deck. Incidentally, I was told by my colleagues from Stanford that part of the reason why Mike was hired as an assistant professor many years ago back now was he has this experience working in the field, controlling traffic and firefighters and all the relevant departments he has to deal with as a graduate student. And every one of the applicants for that faculty job, there are hundreds of them, and they are very highly qualified, but nobody has his qualification that he has worked on the bridge deck with many different departments, with contractors and so on. And that was valuable experience. I also learned a lot from the experience. So that was 2005. And we have monitored, so actually we have done monitoring, but these pictures were taken from Google Maps, and they seem to show very nice conditions. Now, this is the heart of Mike's PhD thesis, was to calculate how much savings we can achieve by using this new technology, a materials technology, but resulting in carbon emission reduction. How much? I mean, we can always claim it's a lot, but how much can you measure it? And he did. So this was work done by him in coordination with a group of another department known as the Sustainability Department. And they specialize in this kind of metrics measurements. What I'm showing you here is a very simplified form. This is the conventional bridge deck showing the amount of carbon emissions by for different reasons. So the yellow part, it belongs to the material, embodied material, as well as repair during the 60 years we assumed service life for this bridge. And there is also carbon associated with construction, which is very tiny bit. But the biggest one comes from the change in traffic. The delta traffic relates to the change in traffic associated with repair events during the 60-year service life of that bridge deck. And the traffic means the tailpipe emissions from those traffics. So we use traffic models that tells us when you have a closure of that bridge deck, how will the cars, the vehicles detour? How far do they have to travel to get around that bridge? And use that information to compute these numbers. So these are not arbitrary. These are actually fairly detailed work that was carried out. And what is interesting is that when you use ECC for that particular bridge deck, we saw a reduction of 40% in carbon emissions. Most of it comes from the reduction in the red part because you have less repair events because the durability, I just explained. But so to our surprise, there was also a reduction in the yellow colored portion of these two bars. You can see that the length here is longer than this one here. And that's related to the materials. But if you had been doing research in ECC, you would then argue, how is that possible that we use synthetic fibers, polymer fibers in ECC? And polymer is energy. It comes from crude oil, and it has carbon emissions. So how is it possible we can reduce the materials portion of carbon emissions for this bridge deck? Anybody? I'll throw that out to you as a question. Give me a chance to have a sip of coffee. So how is that possible to reduce the carbon emissions for this bridge deck when we switch from a conventional concrete to ECC? Given that the material is actually, especially in those days, it has improved a lot. We have greened the ECC, and I'll show you some data in a moment. But change in volume in what? Change in volume of what? Of material use. Yes, continue. You get most of it correct. But let me just emphasize the point. During the service life of the bridge deck, remember, there are less repair events because of durability. So we didn't change the geometry. Actually, there was no bridge. In this case, sorry. So for this conventional deck, there was the conventional expansion joint, which uses steel. So we did count that. But here, we switch the steel out and replace some of the adjacent concrete with ECC. Okay, so but the main saving comes from the operational part due to the improvement in durability and reduction of repair cycles. And therefore, we end up over the 60-year period, the amount of material use is less. Okay, so this is the reason why I said focus on the infrastructure. Okay, if you ask me, what is the carbon footprint per cubic meter of ECC compared to normal concrete? I would have to tell you, unfortunately, it's bigger. It's not as green from that viewpoint. But we can use that material to create a better infrastructure that is greener because of the improvement in durability, because of the tight crack width, because of the self-repair of cracks by itself. All those things, right? They accumulate to allow us to create infrastructures that are greener than before. Okay, so as I mentioned, the material that we had used on that bridge deck was terrible. It was very brown, maybe so dark brown to black compared to normal concrete. It was not very good in those days, but that was 2005, right? Since then, there was a lot of research going on. There has been a lot of research that reduces the carbon footprint by use of supplementary materials, use of waste materials. And lately, one of my students, just before I retired, he looked into carbon curing as well as other means of reducing the carbon emissions. And he got to a point where he got a new ECC that actually falls below the carbon footprint of normal concrete. So I'm not saying that this is readily available for field use, but what I'm proposing is that it is feasible to at least get ECC equivalent to in carbon footprint to normal concrete. That's totally, entirely feasible. And on top of that, as I just mentioned, when you use it in infrastructure in a clever manner, you actually can create a much greener infrastructure, which is what we care. Infrastructure, not the material. Make sense? Okay, so I have other examples done by other students in my group. And here, this is work done by for Aramco Corporation in Saudi Arabia. And they were interested in pipelines. And they were also interested in reducing or creating a greener environment. And we look at this comparison of pipelines that was conventionally steel reinforced and just ECC with no steel reinforcements. And you can see the difference in the performance under diametric loading. The conventional steel reinforced concrete pipe fracture into 4 pieces. This is the very common failure behavior of pipes, concrete pipes. But in the case of the ECC, even with no steel reinforcement, it undergoes a deformed shape but maintains integrity. In fact, we filled it with water after this test, and there was no leakage. Okay. Now, what I really want to communicate to you is this picture here in terms of carbon emission and cost. And you see that by switching from normal reinforced concrete pipe to the ECC pipe, we can reduce both of these measurements, carbon emission and cost. And the reason is that we reduce the thickness of the pipe wall and we eliminate the steel reinforcement. Okay, so on the per meter basis of the length of the pipe, that's the basis that can be used as a basis for comparison, you can reduce the both the carbon footprint and the cost as well. And very similarly, this idea has been demonstrated for pavements. This is the conventional reinforced concrete pavement, and this is the ECC pavement that is reduced in thickness. So here we actually reduce the material when we install it with just half the thickness of the conventional concrete pavement. And if you look carefully, there are no expansion joints. It's not needed. Okay, the ECC has the ability to experience stretching and compression with no cut expansion joints, and all of those results in savings in dollar terms as well as in carbon. So this kind of work has been published. You can look up the details if you are interested in. Okay, so I know I'm running way out of time. All right, I'll conclude. I promise. Okay. Okay, so basically what I hope to communicate to you, what the main message, there are several of these, but let me start with the materials. So ECC by itself is not green, or was not green, but it can work towards greener and greener versions, and there are progress made on that. And I think at this point in time, we can safely assume that we can create ECC with carbon footprints that are similar to normal concrete, not any worse. But when you put it into an infrastructure, because of the durability and resilient performance, you can actually get much greener infrastructures and safer infrastructures, and also at lower carbon and dollar cost terms. So that's what the last sentence here, the last statement here, is an answer to the question I posed at the very beginning, if you remember what the question is. And that question, the title of this talk is, can we create infrastructures that are more resilient, durable, lower cost, lower carbon, right? And so this is one single material. It's not in separate materials. And I believe that we are on the way to get there. And I'm not saying that we are there already. I believe there is still a lot of work to do, but I see a lot of very able bodies in this room and also beyond this room. And I believe that with your hard work, with your creativity, we can get there. Thank you very much.